question is why they are no longer secure. Now tell me, what is the problem on which RSA is secure? Yes. Based on the problem that you don't have the algorithm, to calculate prime factors of the large number. But you have an algorithm called Shor algorithm. Okay, you have an algorithm called Shor algorithm that gets executed on classical computer plus quantum computer. That means this algorithm has steps that gets executed on the quantum computer. Okay, if they are executed on the quantum computer, you can break RSA algorithm. Okay, so what is that? In order to implement Shor algorithm, what Shor algorithm is doing is, Shor algorithm is not directly taking the problem as finding the prime factors of the large number. Instead of that, it is taking that problem into a different problem. Okay, instead of taking this problem of finding the prime factors to a different problem. What is that different problem? The problem is called period finding problem. Okay, what is actually Shor algorithm is doing? Shor algorithm is trying to find period, or you call it as a period finding problem. What is period finding problem? Is that you have to find a number which is a period. Okay, you have to find a number called period such that f of x plus period is equal to f of x. Okay, for a given function, if you have that period, f of x plus period is equal to f of x. That is called period finding problem. Let us see what is that. So it is this. I have a function. What is that function? A power x mod n. Okay, I have a function called f of x called, where my f of x is defined as a power x mod n. And for this function, my aim is to find a period called R, such that what will happen? F of a comma n of x plus R is equal to f of a comma n of x. I need to find an integer called R such that my f of x plus R is equal to f of x. If I am able to find that R, I can calculate the prime factors. What is that prime factors? Here if you notice, my n is large number, okay, for which I am actually trying to find prime factors. Okay, so if you see here, n is the large number for which I am trying to find the prime factors. A is any randomly chosen number, and what is my function? A power x mod n. And for that particular function, what I am trying to find? An integer called R. That R I am calling it as period. So R is period. Such that f of x plus R for the numbers n and a, what is that I am supposed to get? F of x. If I am able to find that R, I will be able to calculate. If I get factors of n, I will be able to find it. So let us see how it is happening. Okay. So for that purpose, I will give you the algorithm. It will work out. So Now imagine my first step is the Shor algorithm goes like this. The first, what is the number? I have the number n to be factored, in the sense I need to find the prime factors. So this is how it goes. Okay. So first step is the n, then I'm going to choose a random number between 1 to n and call it as k. Okay. I'm choosing a random number between 1 to n and I'm calling it as k. Then calculate GCD of n comma k. Okay, greatest common divisor of n comma k. Then if GCD of n comma k is not equal to 1, then k is factor of n. If GCD of n comma k is equal to 1, then go to step 4. Okay. So imagine if your condition of GCD of n comma k is not 1 is satisfied, your k is the factor of n, then you go back to step 2 and choose a different k. So next what you do is you find smallest positive integer r such that f of x is equal to k power x mod n f of a is equal to f of a plus r for any a. So you are going to calculate an r. Now what is this r? Is the period. Okay, such that for that particular function f of x, you take any a, f of a is equal to f of a plus r. Okay. So how do you find this r? Take a new variable called q and assign q is equal to 1. .2 step is find q into k mod n. Okay. If remainder is equal to 1, then go to step 4.3. If not, set q value as remainder. So what we do is we took a new variable called q and q is equal to 1. We found q into k mod n. If the remainder value is 1, then we go to the next step. If the remainder value is not 1, what we do is we assign that remainder value to the q and repeat it. That means we iterated it. Okay. So also we find how many iterations we are doing. Okay. So 4.3 step. The number of repetitions we made in 4.2 is R. Okay. The number of repetitions we made in 4.2 is R. Okay. The fifth step is, if R is odd number, then go to step 2 and choose a k value, new. Otherwise, go to step 6. In step 6, what we do is define a variable p, which is the remainder value in r by 2th repetition. If p plus 1 is equal to n, then go to step 2 and choose new k. The last step is factors of n are f1 is equal to GCD of p plus 1 comma n, f2 is equal to GCD of p minus 1 comma n. Okay. So this is the algorithm called Shor algorithm. Okay. I repeat, look at the first step. N is the number for which you are trying to find the factors. For that purpose, the second step, you have chosen a random number called k, which is between 1 to n. Then you calculated the GCD. If GCD is not equal to 1, then your k is the factor of n. Go to step 2, find a new k. If GCD is 1, then you are going to step 4. What is the 4? Here you are trying to find the smallest positive integer r, which is the period. How do you do that? You take a new variable called q and assign it to 1. 1 into k, q into k mod n you are calculating. If remainder value is 1, then you go to the 4.3 step. If not, what you do? You got some remainder value, right? That remainder value you are assigning it to q. Again you repeat, which is that q into k mod n. How many times you need to repeat? Till you get remainder value as 1. You are tracking the number of repetitions. That number of repetitions form your period. That is that r value. Okay. Are you going to stop with that? No. If r is odd number, then we go to the step 2 and choose a new k value. Otherwise, what we do is we are defining a new variable called p. And what is that p? How many iterations we made is the R. R by tooth repetition remainder value. Please listen carefully. What is that? Number of repetitions made are R. Number of repetitions by 2. Imagine I have made 6 repetitions. My third repetition, whatever is the remainder value, that I am assigning it to P. Okay. Imagine I have made R number of iterations. R by tooth iteration remainder value I am assigning it to P. Imagine if P plus 1 value is N, again I am going back to step 2. If not, my factors are GCD of P plus 1 comma N is my first factor, GCD of P minus 1 comma N are my second factor. This is the Shor algorithm. In this algorithm, if you observe, what happens is steps 1, 2, 3, 5, 6, 7 are all executed on classical computer. Okay? Steps 1, 2, 3, 5, 6, 7 are executed on a classical computer. The fourth step gets executed on the quantum computer. Okay? The period finding gets executed on the quantum computer. So, remember, number 1, if you have a quantum computer right now, what you can do is execute that fourth step on the quantum computer. Rest are all executes on classical computer. Gets that quantum computer output and find fifth step, sixth step, seventh step and find the factors. If you have the factors, calculate number 1, are there prime factors? I am not saying they are prime factors. You need to check if they are prime factors or not. If not, you repeat it. The point is that on a classical computer, fourth step cannot be done. Okay? Fourth step cannot be done. But on a quantum computer, fourth step can be done easily and hence you can find the factors. And once you find the factors, what happens is, once you find the factors, you can find prime factors and then break the RSA algorithm. Okay. Now, how it is done is that number 1, as I said, in quantum computer, you need to have quantum qubits, then quantum gates. Once you have the quantum gates, the period finding can be done with the help of quantum Fourier transformation. You know Fourier transformation? Quantum Fourier transformation, with that help, people can find the period. You can try this example. It is this. I don't deal this one. So take an example. I'll just give you quickly. Imagine n is equal to 15. N is equal to 15. My k value I have chosen is 7. Okay. K value I have chosen is 7. What we are doing is actually f of your, what is the, this one is f of n comma k over 0. If you take, I am doing k power x mod n, right? K power x mod n. So 7 power 0 mod n. What is the value? 1. Similarly, you take f of n comma k 1, you get 7 power 1 mod n. What you get? What you get is 7. So f of n comma k with 2 is 7 square mod n. What is n? Is 15. You get 4. then 7 cube mod n, which is you get 13, 7 power 4 mod n, which you get 1. What is that you got? You got 1 get repeated, right? So every 4 repetitions you get 1. So R value is, I'm just giving you R value is 4. R value is 4. The period value is 4. Now, what is the P value? P value is R by 2th repetition. R by 2th repetition remainder value. So that means 4 is my P value. Okay. So I don't take this one. So 1, 2, 3, 4. So my R value is 4. It so happened here that your remainder value is also 4. This is number of steps, repetitions. This is the remainder value. Okay. You understand? So even you can try the numbers maybe later. You can see if you take these numbers, n is equal to 357, k is equal to 205, you will see all combinations that are discussed in the algorithm. What are all the combinations? Number 1, choosing a k value, GCD of n comma k value, if it is not equal to 1, then that k value is the factor. So in this case, you will find that conditions getting satisfied. So you have to choose a different k value, which is, I think the example that I have noted is k is equal to 52. If you take that k value, then you will see the steps goes. Okay. So try, you will be able to understand the algorithm per se. But now the point is, the whole algorithm, is it that the whole algorithm goes for the quantum? No, only that particular period finding value. The reason is that because you are exploring, it is simple, you are exploring, here how many possibilities you got is 4. With qubits in a superposition state and entangled, you can find all these combinations at a time. That's the huge advantage of quantum computer. Otherwise, what you are doing, you are going one by one, right? In quantum, all these things can be executed at a time because you have a qubit that are entangled. All qubits can work at a time in parallel and explore the whole huge large space. See, we have taken only 2-digit numbers. What is that actual scenario we are exploring? Digits of 100 in nature, 100 digits number. This is only 2-digit number, right? What we are talking about is 100-digit number, 200-digit number. Then you can think of possibilities that you can get. And all these possibilities at a time they get explored. So massively you can solve it. So only that particular step goes to the quantum, not the remaining steps. Once you find R, again you come to 5, 6, 7 at classical computer. So how do you achieve this? Getting this whole space into the quantum is through quantum Fourier transform. This is the logical architecture to implement the Shor algorithm. So this is possible if you have, number 1, again, what is the current available quantum computers? They are all NISQ quantum computers. What is meant by NISQ? Noisy intermediate state quantum computers. If you have access to even these noisy intermediate state quantum computers, they are with 50 to 100 qubits, not more than that. But if you really want to actually break an RSA algorithm with 1024 bit, 2048 bit, you need an actual quantum computer. Is it that readily available? No, it may take another decade, or in the sense by 2030. But the point is that if we sit till 2030 expecting that realization of a quantum computer, and we try to build the